Dear participants, welcome to Section 2. It is my pleasure to introduce Professor B.V. Reddy to this FDP. Dr. B.V. Reddy is a professor in Department of Automotive, Mechanical and Manufacturing Engineering, Faculty of Engineering and Applied Science, Ontario Tech University of Canada. Prior to this, Dr. Reddy is also worked as Associate Professor in Mechanical Engineering Department of University in New Brunswick, UNB, Fredericton, Canada. He received his BTech in Mechanical Engineering from Nagarjuna University, AP, India. Dr. Reddy received his Master's and PhD degree in Mechanical Engineering from IIT Kharagpur, India. Dr. Reddy research interests are in the areas of natural gas, coal, biomass, energy systems, exergy analysis, food as bed combustion, waste heat recovery, and alternative energy sources. He had led funded research projects in the area of food as bed combustion, energy systems, energy efficiency improvement, and biofuels. Dr. Reddy has published more than 300 technical research papers in various referred journals and conference proceedings. He has also contributed book chapters along with his research collaborators in thermodynamics and energy systems area. Dr. Reddy has delivered keynote and invited presentations in international conferences and seminars in many countries. Dr. Reddy has also received the Best Professor Award in Teaching Excellence 5 times in both India, that's VIT Vellore, and Canada, UNB, Fredericton, UIT, Oshawa, Canada. Thank you, sir, for accepting to this giving this talk to this FDP, 6 days FDP. Now you may proceed, sir. So, Professor B. Reddy, sir, please share your presentation.
Yeah, I will share. Just before that, I want to thank Professor Srinivas for the kind introduction, and also this ATAL FDP for the opportunity to share some knowledge with the participants, with the intention that it benefits them for their research growth and for a little bit of development. So before I share it, the way I prepared, as you see, I try to give you the developments in the field, so that way it is going to be more beneficial to you instead of picking one journal paper and going over the equations. Okay, so now I'm going to share this. Okay, so good. I mean, it is now almost close to 8:30
Yes,
in India now. You know, it is morning. It is 9 in 10 in Canada. Okay, so I still probably will take 1 hour 15 minutes to 1 hour 20 minutes, the way I planned.
Yes.
As you have seen your FDP title, which speaks more about thermal, polygeneration, multi-generation. When I thought I will focus more only on climate change sustainability, but I thought I will change my topic in a way that suits to the title of the workshop. So that's where I put the advanced and developments in multi and combined technologies. So as you can see, yeah, you can go to the next one.
Yes, sir.
Yeah. So as all of you know it, though my talk is going to be in a way, I try to give you some research, investigations, even what we conducted with the collaborators, our fellow students or postdocs, but what is happening in the field. Because reason is, you as a participants, you could be PhDs, you could be masters, you could be professors from other institutes, or there could be some from even industry. So the whole idea is, where are we headed and what reasons makes us to look into for different options or different opportunities, and ultimately to address what is called the climate change or sustainability. So if you look on that aspect, though we talk more about reducing emissions, that is our priority is. Now the other side, if you see worldwide, probably leaving a little bit during COVID time, in general, the energy growth is happening because it is due to population growth on one side for the globe, and many countries are trying to develop at a faster rate, particularly many of the Asian countries, even in Africa, and particularly if you take like India and China. So overall, this leads to more energy demand. Then from where it is coming, I don't think it is happening all from renewables. Yes, we want more renewables, but renewables are contributing, given the total, given the growth, there is still a lot the fossil fuels contribute. That means whenever you are talking about fossil fuels, there are emissions, there are other issues that are associated. Then how to use them, but still with the minimum impact? Or is there a way even to minimize that completely? That's where the focus of this whole presentation is going to be. Yeah, next one, please.
Yes.
Okay, if you look into this slide, all of you, my whole point here is, if you notice, these are put for, this is a data, from World Energy Outlook, and there are also a lot of departments they survey time to time. And even if you look, this was for 2000, this is what is projected for 2030, and also there are some more coming up even for further. So the thing that we need to notice as researchers or professors or people involved in the thermofluids or in general engineering side that involves this field. So even if you look in 2000, please look, typically the energy share of the globe is mostly taken, majority of it is carried by coal, oil, natural gas. There are others like hydro, nuclear, renewables. And even if you look the projected one, I'm not saying these are exact numbers, but there is a lot growth in renewables and whatever addition that could be happened with nuclear and hydro in selected countries. But still the interesting thing is, we talk a lot about reducing the coal, oil, natural gas, but still their share is still going to be significant. That means, and then time to time, as you see, when major countries, depending on how the political system comes, the system has also impact. So the previous US administration had a different view. Now the present administration thinks it's more time to go after again oil, gas, and use more of those resources. So that means again there will be more demand for them, more utilization of them. So overall, if you see here, still the coal, natural gas, and oil are going to contribute in a bigger energy mix for many countries. Okay, so that demands that whatever technologies or whatever research we are doing, we need to do in a way that how to bring down emissions, how to improve their efficiency. Yeah, next one, please. Srinivas, can you go to the next slide? Yes. So what I thought was, instead of straight away jumping into combined and other related, in going to the what you call typically where multi-generation systems are now being conducted, that's where the growth is. I thought it's a good to look at where we started. This is, don't think I'm not going to speak on this much, because this is what typically we try to teach to energy students or in general in thermodynamics. People even today conduct a lot of research. Don't think that people are not doing research. They are doing. This is a typical steam power plant system, so which operates on modified Rankine cycle. So we have a boiler where fuel is burnt like coal, solid fuel. So we have a turbine, turbine with many combinations. Then you have a condenser, all these things where generator is coupled. So whether it's a feed water heaters, whether it is optimizing still the temperatures, materials, blades. So people do research. But what we need to notice here is, this basically operates on one cycle, a modified Rankine cycle, where the efficiency is limited by a lot of the limiting factors, whether it could be materials, operating conditions, etc. Okay, so can you go to the next one? So this is what, as I said, there are people, including even, many people from industries to universities. There are still people doing research on cycle configurations, operating conditions, steam parameters, blade conditions, advanced materials role, all these aimed to improve the efficiency in a way that means the emissions will come down or economics will improve, many other things will favor the system. Yeah, next one, please. I think, can you put the next slide before we come back to this slide, Srinivas? Yes. So if you people can notice, this is a typically a combined cycle power generation. So what is the thing that you notice here is, so this is a gas, I mean basically a compressor system, please, with intercoolers, all the combinations. So this is basically a compressor. So air is drawn, air is compressed, and then this is a gas turbine system, high pressure, low pressure. So this is a combustion chamber. So what you notice here is typically, not oil is used. Mostly it's a natural gas or a gasified gas. So, a solid fuel gasified and cleaned, which is going to be burned. So if we take, this is the compressed air, a natural gas is going to be supplied depending on the type of these gas turbines. If it is a GA, a particular make, the latest one, what is the temperature conditions they can operate. So we control the air fuel ratio in these combustion chambers. So when the air fuel ratio is controlled, the gases that are leaving, their condition, the pressure and temperature is such that meets these gas turbine blade requirements. So what you notice is air is compressed in a compressor system, natural gas is added, air fuel ratio is set in a way that meets these gas turbine requirements. And we are expanding the gases in the gas turbine system. In this case, it is expanded to an intermediate pressure. Again, there is a reheating. Then again, there is expansion. So this is where the generator is going to be coupled. So this is basically a gas cycle. Okay. So the generator will try to produce power. Then what you notice is from thermodynamics, when the gases are coming out, because these gas turbines are so advanced, the gases are at very high temperature. So we can't waste them as per second law. Even if we try to use part of the waste heat to heat the compressed air, that's not the best way. So what is done is these gases are waste hot gases are taken through a unit called HRSG, which stands for heat recovery steam generator. So here, water is sent at a particular pressure in the opposite direction. So basically it's a heat exchanger with economizer, evaporator, superheater, all the combination, which is known as HRSG. So the whole story is part of the waste heat is recovered from these gases and steam is produced, superheated steam. The steam drives a steam cycle, steam turbine followed by condenser, feed waters, all the things. So that means this is a steam cycle. This is a gas cycle. We are firing the energy. Our energy source is given at one point. Our energy is fed in the top cycle. So we could generate power here in the gas cycle. We could also generate using steam cycle. So basically, by using this HRSG, we are coupling them in a way that this is a combined way of generating power. So this combined cycle, if any one of you, if you have seen your power plant cycles, books or courses, if you assume approximately eta1 to be efficiency of this one, eta2 to be the efficiency of this one, thermal efficiency, if you derive an expression using combined heat engines approach, the overall efficiency of this combined cycle is eta1 plus eta2 minus of their product, eta1 times eta2. Even if they are individually 0.3, 0.3, that means 0.3 plus 0.3 minus of the product 0.09, which is 0.51, 51% efficient. So meaning is combined cycle way or combined cycle system will generate power at very high efficiencies. So now if we are talking natural gas, which is basically mostly methane, 95%, 95.6%. So at least by having higher efficiency, we can bring down the CO2. So if it is a natural gas, yes, it can be operated this way. Now we are not talking about just generating power. Those are the days 15, 20 years before when CO2 was an issue, not an issue. People never bothered, but now it is an issue. So that means that needs to be addressed. So one way is improving efficiency, but are there any other options for this type of systems to bring down the efficiency? So to bring down the emissions. So now if you see, there are a lot of combinations, advances that are happening. And even on this, a lot of people do a lot of research. Even I'll show you later in the second part of my lecture, little bit on the exergy side of details conducted by this master student long back with me. Next slide, please. Yes. Oh, Srinivas, can you go back to the previous one and previous? Yes. So if you are wondering why these combined cycles are growing worldwide so popularly last 15 to 20 years, almost more than 20 years, their growth is exponential. The main reasons are number one, their efficiency is very high. So when efficiency is very high, for whatever the fuel that we burn, even if it is natural gas, emissions will go down. And that's what you see here, low emissions. Also, depending on what sort of combination you are thinking, if it's a natural gas, typically they take less time to construct this type of plants. So overall, when efficiency is high and the economy is going to be favorable, we are not accounting emissions role at this point. Okay, yeah, please, next one and the next one. Yes, no, the previous.
Okay.
Yeah. So now, if you are, keep in mind, this is how my approach is. If we are attending any workshops are typically aimed to give not one equation and how to solve that equation in depth and get results. So they should give you sort of areas where developments are happening, opportunities are growing, so that depending on whatever role you may be, some of it at least will help you. So that way, whatever the combined cycle I was speaking, people are doing research, people are publishing, and then if you think as a participant, what is that I will benefit other than just listening? So there is a lot research opportunity in these areas. So as I was saying, if it is a natural gas fired combined cycles, now how to address to bring down the emissions? So that means, is there a way to co-fire? So yeah, natural gas and biomass co-firing can be incorporated. Yes, I'll show you some of the work conducted by one of my postdoc in few minutes. And you can have different, also looking at different operating conditions, plant combinations, and to see how the emissions will reduce, what impact it will have depending on what sort of biomass we are using, and the economic studies. So whatever the titles you see here, all these offer research opportunities. Given the little time that a presenter will have, like 1 hour, 1.5 hour, they can't show all the research or papers. But I do share a lot of paper title links or titles with Professor Srinivas later, so he can circulate to interested participants afterwards. Yeah, next one, please. Yes. So if you notice this one, I had shown you a natural gas combined cycle. I explained what the benefits associated with the combined cycle, what research people are doing, whether it is energy, exergy, supplementary air, parameters, many things. Then I showed you why we need to think of utilizing biomass, because as you know, biomass is a carbon neutral. Whatever CO2 it releases, it captures back when it is grown. So typically it is considered a carbon neutral. So if you notice in this particular schematic diagram, there may be a lot of components. So this is a combined cycle. Whatever you have seen earlier, in a way, it is a modified. So what the modification is, if you notice, this is again the compressor system. This is the gas turbine combustion chambers, high pressure, low pressure. This is where you see, again, natural gas is taken as a fuel. So this is the steam cycle where you have the multi-stage with all those things, condenser, evaporators, all those things. So this is, the generator for the gas cycle, for the steam cycle. So you are going to see now an additional unit that is brought into picture. This is called supplementary firing. So here biomass is going to be fired. So the way this system is a lot of research going on, as I said, is so when the compressed air is coming from the from the compressors, okay, this, instead of sending it into the natural gas combustion chambers, this is sent through heat exchanger tubes through a supplementary firing chamber where biomass is burned. So we are trying to recover part of the heat from the biomass to heat the compressed air from state 4 to state 5. So that means for a selected gas turbine design, which is temperature set at T6, P6, the pressure. So when T5 is greater than T4, we burn less fuel here, less natural gas. So that means from emission point of view, this is going to be a major benefit. And if you see again, this is where the exhaust gas is coming from the gas turbine. So if you people have noticed, whenever you do the research and do the calculations for combustion chambers of gas turbines, typically, I mean, whatever we do is they operate with very high. That means there's a plenty of oxygen available. One can check it. So these gases, when they are going, they have a lot of oxygen. So we can burn biomass. If needed, there could be additional air supply. But what I am saying is this itself is like has enough oxygen. So the biomass is burned. We are using part of the waste heat to heat the compressed air. Rest is utilized to generate superheated steam, reheat steam, all those. So that means you have a steam cycle at the bottom. This is, though representation looks top, but typically speaking, this is what the gas cycle first. This is the steam cycle. Now we have a SFG, which is using biomass. So the story is, it is the same combined cycle. Again, we have a natural gas, but we are now bringing biomass into picture, whether you call co-firing, you call hybrid, whatever the term you want to use, that is fine. But the whole idea is this is a modified form of natural gas combined cycle, which incorporates biomass as a supplementary or in hybrid mode, automatically depending on how much biomass we use, what is the role of it into this top cycle, into the bottom cycle. For the same power combination, power capacity, the emissions are going to have a big impact. They reduce. We need to see economics. What I am saying is nothing is in one statement. You know, it has to be supported by many things. So, I mean, this runs in pages of equations where this was a postdoc who worked with me and another professor, conducted a lot of research. So this was, I mean, it was published in a few journals. So, but the story here is it leads to a lot of benefits. Can you go to the next slide, please? Yes. So again, in biomass, there are a lot of biomasses, you know. I mean, what was done is for selected cases, you know, natural gas is considered. This is how typical natural gas composition is, calorific value. Then selected biomasses were chosen, you know, and whether it is a wheat straw, wood chips, you know, some other wood. And also keep in mind, even biomass, though we say atypical, even it could be wheat husk, rice husk. What is that wheat husk grown in North America? What is grown in India or some other place? We need to do again chemical analysis. We simply can't use what is used in North America same way as in some other locations. So the whole idea is here from research point of view. I mean, analysis was proposed, whether it's the chemical side, thermodynamic side, gasification side, all combinations, whatever is involved. So different biomasses were used and studies were conducted, and it was found that the biomass addition as a supplementary to that combined cycle, which was originally fired only with natural gas, has a significant role in reducing the carbon dioxide emission. That is one of our main concern today. So that means there's still a lot of scope to look into combination of the plant, combination of the parameters, types of biomasses, other things, including economics. So this area still offers a lot of opportunity for research investigations and also for projects and publications. Yeah, next one, please. Yes. So in continuation, as I said, the way I put material is to link one after another. Now I started with natural gas, which is a combined, which is a highly efficient technology, worldwide heavily used. Then I said how to think of reducing emissions. We went on to talk about biomass incorporation. Why only biomass? People talk a lot solar. I know there is a lot of interest on the solar from last 15, 20 years. It is one of the fast growing renewable energy contribution in the energy mix of the globe, and a lot of places that is mostly done through PV route. You know, I'm not talking here PV. Okay, so what is the way that solar can be incorporated into this combined cycle? You know, if we can have a natural gas with solar in a combined cycle mode, that also will benefit because solar is renewable. Then, depending on how we are clubbing it, how it is incorporated, what sort of role of the system, operating conditions, so many things. Then one needs to compare, if it is a natural gas, let us say 600 megawatt plant, if we have a solar natural gas with different proportions, how does the economics, emissions, everything will look like? So that means there is even we did, a lot of people are doing, so there's a lot to do. This is where at least apart from PV, solar can be utilized with fossil fuel power plants in a way to bring down emissions. So that means looking at this comparison. And the last one, if you notice it, as I said, solar is such that it is available during daytime. It is not available nighttime, but we generate power. So that means there is a need to think of even storing solar energy and try to use it like when it is not available, like nighttime. So the whole story is from looking configuration point of view to role of system, modeling experiments too, and comparing to bringing energy storage, all these areas, there are people conducting, industries doing work, publishing, but still from research point of view, from opportunity point of view, still this is an area which provides a lot vast opportunity. Okay, next slide please. Yes, you can see this. This is just gives an idea of how solar can be interpreted with natural gas. Don't think this is the only configuration, please. No, 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 no. You can propose many ways. Even if you go and look in any power plant book in a very primitive way, long back, they thought of using solar energy to heat compressed air. That way you raise the temperature, drive the gas turbine. So, so here the way you see is, this is still the gas cycle. You have compressor, the natural gas, and then the turbine system. So this is where you see the hot gases. So now the way this is the solar concentrated field. So, and through the thermal route, not the PV, as I said. Now, what is done here is, this solar energy is used for the bottoming cycle. This is what is that whole thing, which is heat recovery steam generator system configuration. We are trying to use the solar energy to produce steam, to superheat steam. In a way, we are trying to bring solar energy addition to the bottoming cycle and then do the analysis. I know there are places where these are actually being installed now, and there are pilot scales where people conduct research for comparison purpose. We can get the data for validation purpose too. So the whole story is the way this solar field is proposed, concentrated, is linking with the bottoming cycle. So still it is a combined cycle. One has to do the what you call all the research to look into role of different things, from system to parameters to, all those. But the question is, why should this be only linked to the bottoming cycle? Why can't we use, because we can generate very high temperatures using solar concentration approach. So to heat the compressed air, have even the bottom cycle. So a different ways can be explored, now subjected to, sometime technically we may be seeing things favorable, but economically also we need to see, because if the unit power generated by this system is going to be expensive, then it is difficult to justify. It takes time to bring it down. So what I am trying to say is, from research point of view, not only having a natural gas with biomass as a combined or co-fired mode, there's a lot of room, natural gas with solar in a hybrid. What you see here, again, here there could be many possible configurations, not one. So you may see some work being done, but don't think that is the end of it. No. This is only a beginning. A lot of people are conducting a lot of research in a way to contribute to see the role of different things. Yeah, next one, please. So if you notice, I put combined cycle, natural gas, then I went on to show it's a modification using biomass and the typical work. If I have time, I will click on 1 to journal papers, even I will go over them if time permits, but I will, as I said, I will share all those paper titles with Professor Srinivas so that he can share with you those titles, which you can download from, these days, most of them have access to the journals. Then I went on to show you what developments are happening with natural gas if we want to have solar. So that is a hybrid version of it. Now, if you notice here, this is a different system, but a system still that is going to go with the approach of what you call combined cycle. If you notice, first let me explain. As I said, these are all like typically people spend 6 to 8 months of time in generating a lot of the things. When somebody is trying to speak in few minutes, everything cannot be put. Okay. So what you notice here is, so we have a gasifier. Even you heard something in the last presentation. So a gasifier, So if you notice, this is coal. You know, you can have steam, air, oxygen, whatever it is. So we are feeding a solid fuel. We are supplying air. We are supplying steam. Basically, what happens in the gasifier is a partial combustion followed by reactions in a way, leaving gas. We are trying to convert the solid into gaseous form, a syngas. Then this is going to be cleaned. So gasification itself is as old, but there's a lot research that is happening. There are proven gasification technologies, but still research goes on to improve them, to what you call upgrade or improve their performance. So the whole story is this is a gasifier. We are feeding coal. We have gasifying thing in a way that the syngas that is produced is going to be clean. So now if you notice here, so we have gas turbine combustion chambers, like how earlier systems you noticed. So this is the syngas. What we do is we can know its chemical composition. It can be, we can estimate through chemistry knowledge or through combustion knowledge, the calorific value. So that means now once we have these combustion systems, the gas turbine combustion chambers. So what you are noticing here is, please pay attention. This is the compressed air system with intercoolers. So compressed air is, the air is coming through the filters, air is compressed. Now this is the combustion chamber. In earlier case, we used to talk about natural gas. Now we are not talking about natural gas. We are talking about feeding the syngas, which is coming with a particular calorific value. As I said, it can be estimated from combustion knowledge or from chemistry knowledge. Now, I will leave for a moment this one. I'll explain afterwards. So if you see, this is you need to wait. So this is high pressure combustion chamber. This is the low pressure. This is a high pressure gas turbine, low pressure, so multi. So now for a given our selected gas turbine configuration, we are burning the syngas here, and then we are running this system. So there is a generator. So that means power is produced. So notice few things. So this is the waste gas that is going. As I said, whenever air is needed, we feed air here. Okay. So, this will also have some oxygen, we do analysis. So the whole idea is now we are incorporating what is called an additional combustion chamber here. And this is based on a fluidized bed concept, because the fluidized bed has a benefit. There are additional advantages associated. So, whether we are feeding char from here, we are feeding extra coal or even biomass. So I could not put 2-3 diagrams because of the time limitation. There were modifications. So this additional unit, which is a fluidized bed based, is such that we are burning additional fuel here. Now, if you notice, this is the compressed air. This compressed air, which is sent through heat exchanger tube so that it gets heated. That means when it is coming to this point, whatever the number you have, 5, this is at higher temperature than 4. So meaning is less syngas is needed. So again, this is utilized to produce steam, superheated steam, reheating, whatever. So that means we have a steam cycle where power is generated. We have a gas cycle where power is generated. Now we are not using coal, please. The reason why I showed you in the beginning, second figure after showing you the energy statistics, I showed you a steam cycle power plant from Moran Shapiro book. It is not that you people don't know. No, you people know it. But what I am saying is that utilized only coal in burning. Here, the coal is not fed in solid. It is gasified. It is cleaned. So that means we can utilize gas cycle, steam cycle. We have incorporated an additional combustion chamber here. It could be biomass fired. It could be coal fired. If it is a biomass, it helps to reduce emissions again. And this whole thing is what you call, there is a gasification. There is a gasification followed by gas turbine steam cycle. So we are able to generate power in a combined cycle mode. As you remember, combined cycle is today, combined cycle is the most efficient power generation system in the globe. So a solid fuel can be utilized to produce power in a combined cycle mode using through this gasification route. And if any of you, as we give time at the end for questions, if you think what gasification is, technologies, this is a well-proven place. I know there's a lot of research goes on, but there are a lot of details available. As I said already, we supply coal and supply oxygen, air in a way, partial combustion followed by reactions, leaving ash will produce syngas, and it is cleaned. Though the cleaners are not shown in this particular diagram, we don't send it. Otherwise, these turbine blades will be gone because of the particles. So it is cleaned, then it is burned. So the whole story is this helps to operate in a combined cycle mode with solid fuel, where efficiency is going to be very high. Whatever we talk about reducing emissions and producing power with efficiency is met by this system. So that's why there is a lot of research goes on. There are plants too. But not the way they should have been. There are power generation systems around the globe. Some of them operate on this concept, but a lot of research is happening. And if you see generally, a lot of times when people show this, they simply put it as IGCC. So what it stands for is, CC stands for our common, very popular combined cycle, integrated gasification. So there's a gasification, entire system is integrated. So this is called IGCC, and a lot of research goes on. Even we did a good chunk of work. And again, this was one of the postdoc who did good work, and this got published, in many journals. I could not put many figures, but this is one of. Now, if you are thinking as a participant, so what is there? There's a lot to do research, please. Whether it is thinking of biomass, thinking of configurations, thinking of gasification agents, or looking at the overall impact it will have, including emissions. So there are more opportunities. Yeah, next one, please. Yes, that's where I put it in brief. As you can see, from gasification to doing system analysis, parametric modeling, thermodynamics, and looking. Oh, this one I won't talk here. The hydrogen, I have another system where I'll be talking. But this is, as you people know, hydrogen is now one of the very popular growing energy technology where there's a lot of attention paid. Okay, so which I will be discussing a little bit. And supplementary role, as I said, instead of coal, if you use biomass, there is a role to reduce emissions, CO2 particularly. Again, type of biomass has impact, and many other. And as I said, you have seen here energy analysis. There is also exergy, which I'll be speaking at the end. The exergy in general, why it is getting so popular. There are people who are doing a lot of exergy research, and Professor Srinivas is also one of them. So in India, so what you see is, why does it become popular? And that also I will explain. So my whole point is on a way to motivate you people. If you have a systems like this, even if you consider a piece of it, and if you try to do some contribution, like, what is that novel, what addition it contributes to what you see in the literature review, you can end up publishing in high-end journals. Okay, so there's a tremendous room, scope, whether to get an industrial project or a government project to publishing. Yeah, next one, please. Yes, so this is, don't worry. In a way, you can't read it. It's a hard on a screen to read, but the idea is, again, this paper, Professor Srinivas himself can give you the paper details for you people if any one of you are interested. So this is before I speak about the paper, before I speak about that little bit diagram, which is again a power generation system, keep in the way I am approaching. First, I started with steam power plant, a modified Rankine cycle. Then I went on with combined cycles, various configurations of combined cycle, including up to gasification of coal, where I was in the last few slides. So what you are noticing here is, as the heading says, this one, Professor Srinivas conducted all the work with biomass gasification. But the whole idea is, this is not anymore combined. If you notice the heading, it takes to the what is called triple cycle. So that means, you have seen heat engines, now we are not talking about 2 heat engines. We are talking about 3 heat engines. Heat engine 1 heat rejection becomes heat engine 1 rejection becomes input for heat engine 2. Its rejection becomes input for heat engine 3. Okay, again, there will be heat rejection to satisfy second law. So the story is here, if you see, there is a biomass gasification followed by gas cleaning with with gas turbine cycle for power generation. Then you are seeing a heat recovery steam generator, and all the things that you are seeing here is, okay, this is the steam cycle with many combinations. See multi-stage with all those, though it is a small in the diagram there. Then you are seeing what you call here a different cycle, which operates basically a Kalina cycle. It is a low temperature fluid operated cycle, vapor. So this is a Kalina. This is a great person called Alexander Kalina. I think in 1983 proposed this one, and it is used in some chemical industries to generate power using this approach. But theoretically speaking, so you have heat engine 1, 2, heat engine 3, or in a way, this is a triple cycle. So if we go by thermodynamics, if any one of you have, seen, just put heat engine 1, 2, 3, go by the typical thermal efficiency definition, try to define its overall efficiency. I can't spell it, it's too many terms. So what you see is thermodynamically, yes, it is very favorable. Now, we can't simply go by thermodynamic efficiency alone. So you have to see economics, you have to see many things, including the role of gasification operating. So this particular paper gives a lot of details about with how to do biomass gasification, followed by the analysis, whether from energy, exergy, and bringing what is called a triple cycle approach. So this is, I think, one of the very recent paper. So which is basically, a joint work done by Professor Srinivas, me and another professor called Professor Gupta. Okay, so the whole story is now from a Rankine cycle to combined cycles and a lot of modifications, the way research is being conducted, a lot of scope that is available, to now we are a triple cycle. So if you see this here, virtually there's a lot of area, a lot of room available. Why only biomass? Why can't we have a solar here? Or why won't we have some other thing? So there are many other possibilities. So even these details available in this paper itself will take 1.5 hours for someone to explain. So as I said, the whole idea is to give you the developments and the scope. So you can see here the triple cycle and the possible advantages associated. And thermodynamically, no doubt, when you propose an equation, you will see it's a beneficial, but we can't go by that only. We need to look into economics. We need to look into other things. That's where a lot of research is happening. And keep in mind, I'm telling you, whoever publishes, whether it is you or me, we publish very little details, please. So you have to look many papers, many reports, many data before you can come up with what you call something that you can have a complete knowledge, complete details on some system. Okay, next one, please. Yes, that's where I already gave summary of what part of the work about that, but it is, as I said, gasification, thermodynamic analysis, the role of what you call the Kalina cycle, and the parameter supplementary role. All those were investigated in the paper, which is, again, you can obtain the paper once you have the title of it from Professor Srinivas afterwards. As I said, I'll give remaining papers too. Yeah, next one, please. Okay, so now I think slowly, just give me a second. We are slowly heading into the next stage discussion, where virtually very little research is done. That's where a lot of opportunity or vast opportunity. So from a simple, from a what you call the steam power plant, typically in 1880s, so later combined cycles, then I said triple cycles research is being done. Okay, we will see that type of systems. Maybe it may take time. Now we are talking about multi-generation energy systems. Now the question is, why are we interested towards multi-generation? Keep in mind, conducting research, whether you are conducting through theoretical way, thermodynamic way, modeling way, or you are doing experiments. So we always will have some system in mind and some objective in mind. We conduct, we analyze, we come up with conclusions, and then we publish. But the thing is, sometimes it is also good to know, like in a broader picture, the developments and what developments will happen in the future. So that way, sometimes it's good to go in areas where there's more opportunity. So now these multi-generation energy systems are gaining popularity because, in a way, in many cases, not only we can improve the overall performance, there is also possibility to have what you call the usage side products or benefits. So I could not put in combined cycle because of time limitation. There are some countries in the world that was planned, say there are few cities nearby, or there are some industries nearby or within a thing. So you can also incorporate cogeneration. It is not only generating power using gas cycle, steam cycle. There are industries, or there are some cities, what they do is at selected times, some low pressure steam, or even the condensate is utilized, the waste heat, to heat some feed water heaters, or to heat some homes, or to heat some industrial processes. So converting, it's not just only a power generation, it is also doing some process heating side. So that means it is a combined cycle cogeneration, which is again a combined system, but involving additional what you call usage into the system. So in multi-generation, that's where we are looking at multi-side of benefits from the same energy source. So I think this is where I think last few years people talk a lot, people are doing a lot of research. So, I mean, it's not that in the lab we can conduct a multi-system experimental setup and do everything. It's not that easy, given not only cost and maybe side. So it can be, systems can be proposed, they can be modeled using thermodynamics first, and one can look into role of different parameters. And depending on what fuel, what source you are talking, if it is a solar, you don't need to worry about emissions. If it is something like coal or natural gas, you have to worry, because these days emissions are an issue, or emissions are our priority. Yeah, next one, please. Okay, I will be taking what you call a reasonable time here, though it is not. This is a system taken from a particular journal paper, though, I mean, even a lot of researchers do conduct. Even I have some work, even Professor Srinivas has some work. Instead of putting my own system all the times, I choose to take from a journal from a different author. Okay, I think this is one of the earliest, probably one proposed by the author. So notice here, I mean, I will try to explain the purpose of the way the system is proposed. You will see the beauty of the system, what benefits it tries to propose, and a lot of the things are still yet to be investigated. So that means we have more, maybe many more question marks. Okay, so if you notice here, I mean, it's basically a multi-generation system, please. And people have different names. Don't worry, multi, poly, whatever it is not. It's in a way I put it, you have a multi-system. So this is basically a gasifier. So we are talking here typically coal or biomass. I know there are other things also put into picture. So now the whole aim is to gasify a solid fuel. So now whatever unwanted things, these are going to be taken out, particularly ash, or that cannot be gasified. So if you notice, so the way you have here is, because whenever we are gasifying a solid fuel, when the syngas is produced, because as I said, gasification, though a lot of research goes on, it's a well proven, there are technologies available. So once the solid fuel is gasified, let us say it is coal, so we need to clean it. There was a time, I think in probably 15 years before, the cleaning took a lot of time to understand because of many challenges it posed, the gas cleaning. So now I think there is a well-developed gas cleaning systems. So this syngas is going to be cleaned so that we don't want any particles, because they will harm later the turbine blades as they go through different systems. Now, I mean, as I am telling you, this is again a sort of a configuration proposed. Don't think that you need to go by everything the way it is. You can come up with your own way, but still meeting multi-generation objective or concept. So there is a cleaning up of those particles. Then the way this is, I mean, uh, if you notice, we are not talking here combined or some other. So the gas that is typically solid fuel that is gasified, when you see the gas that is coming out, it will have different gas components. There will be hydrogen too. There will be many other components. So what is the needs? Depending on the purpose, some of them will be removed. So that means, there is a way even to produce some useful chemicals. So if even time being you leave this, so this is the gas is cleaned, separated. Now, so there is a hydrogen separation approach. How to separate it? Yes, there are ways to do it. I may not be presenting here everything, but if you go and look, or if you listen to some other expert, they will present. So the idea is hydrogen separation is an option. Then CO2 can be even separated. So you will see here, CO2 separation. What happens afterwards, I'll talk you what can be done. Then you can have a gas afterwards. So now if hydrogen is separated, as I said, whether we are going to use the hydrogen as it is, we store and use it for some other purpose, or are you going to use on the site with fuel cells so that power can be generated, or the gas after hydrogen is separated or some other components are separated with a known calorific value which can be estimated. Now we are going to take it to a gas turbine combustion chamber where it is burned in the traditional way. We have the generator where power is produced. Whenever you are talking about a gas cycle means modern days, these days, it is a high temperature gas turbines. So that means when you see the waste gas coming out of the turbine exhaust, it is at high temperature. So then we are not going to throw it. Second law wise. So then we are going to send it to a heat recovery steam generator where we circulate water at high pressure, produce superheated steam at high pressure, run steam cycle. So that means if you notice here, this is the steam cycle which is producing power. This is the gas cycle which is producing power. This is what links these two, which is we are trying to utilize part of the waste heat. Some waste heat is going to be lost. We are able to produce hydrogen. Whether hydrogen is going to be used for some other applications, hydrogen has a lot of demand and applications, and are through fuel cells. So if CO2 is captured, what happens to the CO2 chemicals? So the way this whole system, if you are seeing, please observe here we are talking typically a solid fuel. Then we are talking a gasification route. Now we are not talking about simple power generation. Even if it is power generation, we are talking through combined cycle, which is highly efficient route. We're talking about hydrogen. We are talking about fuel cells. So the whole way, if you see, maybe in this whole system, even somewhere, if there is a room, we may be incorporating a process heating heat exchangers or process heating application. So this is what looks the multi-generation system with many opportunities, many outputs. So this is where now the systems are headed in future. And as I said, the advantage is they provide high performance. Now there are a few more. As I said, I'll give you enough time at the end for our interaction. If we are talking about coal here, the question comes, what about carbon dioxide? Even though we improve the efficiency, we improve the performance, we are able to have multi-generation. If CO2 is there, how to address it? So, I mean, there is a way to capture carbon dioxide. If we capture carbon dioxide, the only question is, if imagine we are going to have a lot of these type of systems in operation in huge scale, let us say it is a 600 megawatts, then what to do with the CO2 is a question. Do we want to utilize the capture CO2 for some applications, maybe to grow algae, then biomass, and then produce biodiesel? Or do we, there are some, researchers in University of Waterloo, they are doing a lot of research from last 15, 20 years, how to compress CO2 and put it into the ground. But if we put in the ground 2 or 1 kilometer down, if earthquake comes, the CO2 will come back. It will be released. Then our all effort will be lost because it takes a lot of power. So CO2 can be captured. What to do with the CO2? Do we use it for some useful thing? Do we store it? again, all research questions, research opportunities. So lot to be done. But now coming back to what my focus was, from a simple power generation to combined to gasification coal to, which is combined to triple cycle to, now we are at a multi-generation. That's where even the title of this workshop was well focused. So this is where future systems are headed, with not only fossil fuels, even with solar. If there is a way to generate multi benefit, still it is a beneficial. So as I said, people are doing some research, people will do some on hydrogen, people will do some piece of work. So as such, if you see a system like this, or the concept, a multi-generation concept like this, sorry, I think in my view, even if you have seen few journal papers, if you have come across few research projects people are conducting, so whatever we are doing is very little. There's a lot we need to do as all researchers. It's not about, don't think in research, one person will do everything. No, no, no. If that is the case, the story could have been long back done. So whatever we contribute is very small. Okay. So I think this system is like such that it gives a lot of details, lot of opportunities, lot of work. Yes, people are doing, even we have done some work. As I said, I choose not to put again one of my postdocs or some other students diagram to show. So rather this one is a very good system, tries to give a good combination of the multi-generation route and the benefits associated with a lot of questions. Meaning is there is a lot of research that we need to do to explore and understand a lot of details. Yeah, next slide, please. Yes, this is where for the system that I showed earlier, rather than answers, there are more questions, whether for you or for me. Okay, so we all will have more questions we need to put and we need to investigate. So from modeling experimental to gasification side to looking at different thing, and even what sort of how much hydrogen can be produced, the separation to its economics, and capturing CO2. No, there are, if sometimes you do see when you read journals or you read some latest reports updates, sometimes you may see countries like in a few European countries, they're capturing CO2, they are trying to do something, some byproducts with CO2. On a small scale, it looks very good. But when you are talking about big power plants, not one, two, in huge numbers, if CO2 is going to be captured, that itself is going to be a costly process. What to do with that CO2? I think in US, even in Canada, I think in pilot scale, but in US, I think somewhere for one power plant, a coal-based power plant, they are collecting CO2, they are growing algae, they are producing biodiesel, they are trying to study economics of the whole system, I think last few years. Suppose if things favor, maybe that may be the route where you capture CO2 from fossil fuel based power plants, grow algae, grow, then produce biodiesel, and ultimately making virtually what you call the environment friendly. Oh, I think Professor Srinivas, can you go back 1 minute to the previous slide? 1 minute. Yes. Yeah. I forgot to add two details here. I did talk what I wanted to talk. But if you really look, please, if you look this whole system, if we are going to have this multi-generation to the extent that think that we are capturing whatever the CO2 this whole system produces, and we are able to take care of that CO2 captured. Let's imagine for a moment, I'm not saying it may not be that easy, but there is a possibility, as I said, if algae can be grown and biodiesel can be produced. So if you look on that count, then if you compare, if it is a coal-based multi-generation system with CO2 capture and utilization, with basically no impact on the environment, then this is as good as solar energy system. I'm not comparing economics. If economics also are going to compare, then what is the wrong in it? In future, we may see coal-based systems going through this route when they can justify economically also as, let us say, renewable systems. So that means there's a lot we need to do. That's where the future, whether it's a 10, 20, 30 years, next set of research will happen on all these multi-generation systems. Yeah, next one, please. Yes. So yeah, it's okay. that is where, as I said, one has to compare with the renewables too. I mean, anything these days, I have a paper, at least I will try to glance it quickly, one of my postdocs, what you call a sustainability indicators. So these days, energy systems, we just don't comment on only performance and economics. We also need to look into environment side, which is called sustainable indicators. Okay, yeah. So now, having given at least some information, at least I hope some of that will benefit you people, from a simple power plant system to combined to hybrid to gasification to then went on to multi-generation, with the scope, with the opportunities those and the tremendous research I mean objectives and scope which can be conducted, now I just want to dwell a little bit. You may be hearing later in this workshop maybe about exergy or second law. Generally, when people talk about energy systems, people talk about thermal systems, always they all try to give you some details on energy exergy. So I just will take only 10-15 minutes, maybe 15 minutes, why exergy analysis is becoming popular. This is what you call second law analysis. As I have said, all of us, when you hear first law of thermodynamics, you hear second law of thermodynamics. First law, we do energy balance, and then we come up with something. So why do you think the second law is gaining so much popularity? And don't think that second law suddenly became popularity last 20-15 years. So these laws were framed in 1850s, the thermodynamic laws, they were there. But only thing is, second law is receiving lot attention late 80s. I think probably a lot of credit for that should go to Professor Bejan. Okay, I think he brought out a lot of details related to that. Okay, I know there are all other great professors who contributed, but I think from late 80s or close to 90s, last, I mean, 30 years or so, you see a lot about second law or exergy analysis role. Then I will just dwell on a little bit. What is that second law? What is that exergy analysis? What it extra contributes? How to do it? Okay. So if you, as I said, first law, we make energy balance. Second law, that's where we look into not only direction to process, we look into the role of irreversibilities. You know what irreversibilities are, whether they are mixing, pressure drop, or a reaction, or a lot of other things. So the whole idea is these irreversibilities tries to reduce what you call the quality. So that quality, which is not, I'm not talking about steam quality, please. So the quality is from second law point of view, we are destroying the quality which otherwise could have been utilized. Yeah, next one, please. Uh, I, I think, was there any slide? Oh, yeah. Okay. Oh, I think it comes next. So let me just give briefly. Don't think I'm trying to teach you exergy, because this exergy is these days is becoming very popular. You go to any thermodynamics books, which are very recent books, you will see the procedure well laid out. Once you understand the meaning of exergy definition or term, which I'll explain, conducting exergy or exergy analysis is not hard, please. It is a very time taking. I mean, things have to be calculated properly. I know. I mean, later, maybe I think you have one of the session with Professor Srinivas. He may explain, how much time it takes, because he has done a lot of work too in this area. So, the exergy analysis, to conduct exergy analysis, there is approach. So, as all of you know it, you know how to calculate availability. So that is with reference to the surroundings. Whenever you have a system, let me before I define exergy meaning, before you have a system, let us say it is at a temperature of Ti and Pi. Okay, temperature is Ti, pressure is Pi. By the time it reaches that of surroundings, which you call T0 temperature, or the pressure is, T0, which is, so what happens is, it has ability to do something. By the time it reaches that of surroundings, though there may be potential, but it cannot do anything. It's a dead. So exergy is, the way it is defined, is the maximum theoretical work that can be obtained before a system reaches that of surroundings, which is called reference state or dead state. So, I mean, this is how you can estimate using thermodynamic basics from thermodynamics books, the availability, then the exergy in general like this. Now in exergy, when one is conducting exergy analysis, there are different exergy components one has to estimate. There's a physical exergy, chemical exergy associated with kinetic and potential. Usually the kinetic and potential terms are very small in contribution. So we often neglect them. So it is mainly the physical and chemical one has to account. So this is how you can estimate the physical. For estimating chemicals, there are different routes, whether you use equations as proposed by a lot of researchers are available in thermodynamic books, or you are using some tables. So there is a procedure, there is a way. What I am saying is, I mean, when you listen to only exergy analysis lecture in your workshop, they dwell on in detail about each of them, because I'm just trying to give you in brief. So there is a way to estimate physical exergy like this, chemical exergy like this. Next one, please. Then, as I said already, I mean, we typically neglect the kinetic and potential components given their contribution is going to be so small. This is how at any location you can calculate the total exergy. Okay, so this basically, you are calculating the at different locations. So that means we need to know the physical and the chemical. There is a way, as I said, I showed you in the previous slide, how to estimate physical. Once you know availability, then the chemical, as given by the lot of relations or tables. Okay, can you go to the next slide, please? Yes, now this is the same combined cycle diagram, and I will just try to explain briefly. And if time permits, I'll glance it in 2 minutes even to show you. As I said, I could not put all the equations. Then they will take away 7 pages. But at least I can glance in the paper. This is one of my master student who did long back, a great student, I tell you, did very good work on both energy and exergy for natural gas combined cycle system. So the story is, my objective here is not to talk about this student, just to show you how do we conduct, and where do you calculate physical, where do you calculate chemical, how to be, I mean one should be careful in accounting them properly. So when you look at these compressors, this is the air coming through filters. So we are giving work input, so we are compressing air. Let us at this point, when you see it is compressed to a pressure and temperature. So when you see the condition with reference to the surroundings, so physical conditions are different. So that means they have ability to do something, the air, the compressed air. So you calculate physical exergy, you go by that nomenclature and the equation I showed you, which is available in thermodynamic books. When you see the combustion chamber here, we are sending now the air, compressed air. We are firing natural gas. Then we are getting products. These products, air fuel ratio is set based on this gas turbine requirements. So now there is a change in chemical composition that has to be accounted. That is accounted through chemical exergy analysis. So that is one. Now, like that, we go around the entire components of the system. We calculate physical, chemical, neglecting kinetic potential. We come up with the total exergy at each location. Then we can define how you define energy efficiency, exergy efficiency. I will glance through the paper, as I said, after a few minutes. So the whole idea is, then you may have questions. Okay, well, I know how to conduct energy analysis. What is that I am going to have extra benefit? Or if you are looking from the system point of view, what is the benefit this exergy analysis is going to provide? Yes, there are going to be a lot of additional advantages or additional details associated with the exergy analysis. If we can utilize those results and then we can investigate and modify designs, then that will lead to better design of the whole system, better performance, and that's what we want. So we are not trying to now look into the modification of design just from first law point of view. We are now trying to look in from second law or exergy point of view. Okay, so I'll show you that. Okay, the next slide, please. Yes, this is, as I said, I'm going to put that student one of the paper. I will glance through that through the methodology of that, how story is done. Now, if you look here, this is, I think at that time, probably one of the earliest form of representation of multivariables looking into a role of something. See, we are looking, say, the exergy destruction with pressure ratio, temperature at the same time in a particular combustion chamber. Okay. So how the parameters will influence when you vary the pressure ratio, when you vary the temperature of the gas turbine. Okay. For the I think the main gas turbine unit that was considered. So you can see, instead of just looking at only one way, you can look the role of multi-parameters and their variation on exergy, loss, or destruction. So that will help further to quantify and look into the details. Yeah, next slide, please. Yes, pay attention here. This is a very good, what I call results wise, this is a very good one. This is one of my master students. So if you look here, this is again for a combined cycle system. The exergy analysis was conducted, and the exergy destruction with a set of operating conditions were represented in a way to get some meaning out of it. So if you notice, as I said, any power plant system will have a lot of components. And when you look from energy point of view, exergy point of view, and you can represent their performance. So if you look here, so what you see is, you are going to see, it is trying to tell you that the exergy destruction and losses seems, are very high in selected of these components, which are basically combustion chambers, heat recovery steam generator, where loss, exergy loss. So these are the main combustion, reheat, HRSG. Now, if as a researcher, whether it is you or me, we are conducting, we are getting some results, we will say that this is how it is, and then we can see what benefit it contributes, that it will get published. That's good. But now if you're looking from system point of view, what is that additional thing it is trying to throw out? This exergy analysis, as I said, is, if suppose if there is a research funding available, there is a company willing to invest some money to improve those existing technology to next level, even very little improvement in efficiency. So that money, whatever, if it is given to a researcher, a part of it goes to looking at these modification of these combustion chambers, their improvement, that is going to be coupled with the blade materials. If anything can be improved in these components, we'll have overall system improvement. If I try to use that money to do something here, whatever is going to be done is very little. Here it has a big impact. So that is the advantage of exergy analysis. We can pinpoint components, how they are doing their duty. Then we can see if there is a way to improve them, how much you improve, that will has impact on the overall system. Can you go back to the previous slide one time, Professor Srinivas? Not the one, previous, the system. Yes. So now look, if you compare with my discussion in the last histogram discussion. Now look here, please. So this is the combustion chamber. What we do, if you go back and read literature, go to 70s and 80s gas turbine systems, they used to have very low temperature. The blade material was very poor. So what people used to do when natural gas is supplied, if this can operate, the blade can accept only 800 degrees centigrade gases. That's what its thermal limitation was. Now, when you are supplying natural gas here, people used to supply more air just to dilute it, to bring down the temperature to meet this requirement. So dilution, mixing is a reversibility which destroys quality. Now with a lot of advances in blade materials, nowadays we have as high as close to 1375 degrees centigrade. So that means so much of improvement in the material field when you look into the application on this side. So now we are not going to dilute so much. That means less mixing, less quality destruction. So that means less entropy generation. So exergy wise, you see the benefit. So what I am trying to say is, sometimes thermodynamics, what research we do, what we propose from quality point of view, exergy point of view, may help some other fields to develop first, or what developed in the other fields, then we try to use it. So definitely, yeah, you can go back to the slide where I was. No, the previous one. Yes. So what I am trying to say is, this is just for one system. You don't have to, this for a combined cycle for one set of operating conditions. There are many systems. It is not about polygeneration, thermal generation, multi-energy. Take any engineering system, any system, what you notice is there is a room to conduct research using second law knowledge, exergy knowledge that will provide much benefit. I think I know this is a time restriction is there, but in general, I will use only one word. Sometimes even you notice sometimes whether there are organizations or individuals, you may see, oh, those are very successful people, whether in research or whatever field they are. Don't think that it came just like that. So here the time, one of the time wastage or how we use time is one of the factor. Second law way you can link it. So people who utilize in a productive way achieve much more. So it's all comes down, second law is not just only for engineering systems, machines, it can be utilized for humans too. Okay, so that's what the message I am trying to convey. Yeah, next please. Yes, I think in 2 minutes, I will glance two of the papers before I open the room for questions. So this one is sustainability. There are many people working to develop indicators. Now, if we are going to talk about only renewable energy sources, renewable energy is what meets all our energy demand. There is no need to talk about any of these sustainable indicators because renewable energy is very sustainable, a friendly one. But still, it's going to be a long way. We will be using coal, natural gas, and oil. It's not going to be that easy. We are going to get away from them given our growth, our demand, population, so many. So that means there are people who are developing a lot of these indicators. Again, these are aimed to compare fossil fuel systems with as if it has been a renewable or a completely friendly one. Yeah. Next one. Okay. Oh, yes. So now, if you see what opportunities, now, if you are wondering as a participant, as I said from the beginning, in between, I used to add that. So there is a lot of challenges, lot of scope to conduct research, whether it is in multi-generation systems, integrated systems, whether it's in gasification. Now, as I said to you, because now I think I have a screen sharing problem. Otherwise, I could have put few of the other details. So we talk these days hydrogen a lot. I don't know how many of you have looked into the literature, please. Even today, the hydrogen produced in the globe out of 100%, only 4 to 5% comes from electrolysis of water, which is what is called the friendly approach. Now, the remaining 93 to 94% of hydrogen, 47% of hydrogen is produced using natural gas through steam methane reforming process, SMR, what they call it. It's a very efficient, very cheap way to produce, but there is a issue associated. There's a carbon dioxide, okay? And coal oil also contributes. So now what you notice on this side is there is a room. If we can produce hydrogen using solar or biomass, then we can reduce its dependency on at least coal and through the coal route. Or even if it is natural gas, we need to capture CO2, then look into economics. So the whole hydrogen itself, as people talk that it's going to be one of the future energy, I mean, that's where a lot of attention is going to go. So there's a lot of research to do too. And for any energy systems, so you can conduct the what you call the second law analysis or exergy analysis. The reason why I'm saying you is not everybody will be able to get 50 lakhs or 1 crore research projects. Not everywhere it's possible, but it doesn't mean that we should stop doing research. So sometimes even with limited resources, if you are good in say subject background of thermodynamics, your combustion or whatever the knowledge that you have, and if you are good in modeling and using some packages or generating your code, maybe using MATLAB or some other means, you can propose a system. If you can come up with some contribution that this will do compared to the literature, then you will be able to publish. Then you are going to be having your record of publications to your site. So using this modeling, second law approach, there's a lot room to do even with the very limited funding. Hardly you need little bit of background and some computing source and skills, that's all, okay? And climate change, for this we have to look into different ways, as I said, to the extent of capturing CO2 and to use it. So finally leading to sustainability. Okay, next slide, please. Next one. Yeah. Yes. So I think whatever I try to give, I don't have to say as a separate conclusions. In between, I was trying to give the hints. So there is a development towards more multi-generation and hybrid energy systems. That's where the future is going to be headed, to utilize a lot of these fossil fuels for sustainable living purpose. And this is not only experiments, modeling, simulation will count. That's where not only energy, exergy analysis will play a role. And typically when we are talking about harnessing renewables, particularly solar, given its what you call the intermittent nature are not available during night time, we need to have storage systems. So the storage systems have to be what you call, there has to be research, so how to store solar energy, how to use it afterwards. And from second law point of view, when research is done, that will lead to efficient design of components, overall systems, and sustainable what you call